Topic of presentation is design of rectangular slotted patch antenna array sensor for breast tumor detection. According to the breast cancer projections of American Cancer Society in 2025, 3,16,950 new cases and 42,170 deaths will happen in US, and globally this figure will exceed. The limitations of conventional imaging modalities are X-ray mammography uses ionizing radiations, MRI incurs high costs, sonography exhibits low resolution, and CT scans are not appropriate for regular screening. To overcome these limitations, microwave imaging comes into picture, which offers an economical, intuitive, accessible, and non-ionizing solution for identifying malignant tissues. Microwave imaging operates by leveraging the contrast in dielectric properties between healthy and cancerous tissues. Coming to the proposed work, a 1x4 slotted rectangular patch antenna array sensor is designed to operate in 5.8 GHz ISM band, featuring enhanced gain and sensitivity for differentiation between healthy and cancerous tissues and accurate tumor detection. Coming to the design evolution, firstly, a rectangular microstrip patch antenna has been designed to operate at 6.9 GHz, and then four rectangular slots of length LS and width WS are carved at a distance A from the edge of the patch, which resonates at 5.8 GHz, achieving a 35% of miniaturization. The overall footprint of the antenna array, including feeding network, is 0.96 lambda g cross 2.5 lambda g. A 1:4 equal way power divider is employed to feed each antenna element in corporate feeding network. The performance of the proposed antenna sensor is analyzed in different scenarios. A multi-layered homogeneous female breast equivalent phantom model in CST containing skin, fat, and tumor. The depth of the tumor from the skin upper surface is 10 mm. The antenna standoff distance from the phantom is maintained at a value of 3 mm. In proximity to the healthy tissues, the antenna resonates around 5.82 GHz, while in the presence of the tumor, the frequency is shifting down slightly, resonates around 5.81 GHz. The dielectric properties of the breast tissues are listed in the table. In the next scenario, the location of the tumor is varied along plus or minus x-axis. Results clearly indicate that by moving the antenna sensor away from the center of the breast towards plus or minus x-axis, the operating frequency shifts higher side. In the next scenario, the diameter of the tumor is varied from 20 mm to 40 mm, and it has been observed that for healthy tissue, the antenna resonates at 5.82 GHz, but with increasing diameter, the resonant frequency is shifting from 5.82 to 5.807 GHz respectively. The peak gain of the antenna is obtained as 11.9 dB in free space and 2.1 dBi in the presence of the phantom. Coming to the radiation efficiency, it is 90% in free space and 32.5% in the presence of the phantom. In figure 7, we can observe that the antenna exhibits a directional radiation pattern with the main lobe directed in the broadside direction. The cross-polarization levels are appropriately 20 dB lower than the copolarization levels in both the principal planes. Coming to SAR analysis, for healthy phantom, the SAR value is observed as 1.48 watt per kg for 1 gram of tissue at input power of 25 milliwatts. After introducing a tumor of radius 12.5 mm, the SAR value increases as the distance between the antenna and the tumor increases, reaching a maximum value of 1.59 watt per kg at a distance of 10 mm. Beyond this point, with further increase in distance, the SAR value gradually decreases. For experimental validation, the antenna array is manufactured on RT-Duroid 5880 substrate of dielectric constant 2.2 and loss tangent of 0.001. The phantom is prepared from common materials like Vaseline solution, distilled water, olive oil, castor oil, a mixture of wheat flour and corn flour in different proportions to replicate the dielectric properties of real breast tissues. In this figure, the proposed antenna sensor is placed in proximity to the prepared breast phantom. Here we can observe the simulated and measured S11 response in free space. Figure 10 shows the measured S11 versus frequency response for various locations of the tumor and for different sizes of the tumor. Figure 11 shows the simulated and measured 2D radiation pattern plots at 5.8 GHz for phi is equal to 0 degrees and phi equal to 90 degrees. Finally, a simple low profile conformal structure single port 4 element antenna array sensor is proposed, operating within the 5.8 GHz ISM band. Simulated and measured observations reveal a noticeable shift in frequency in S11 versus frequency response corresponding to variations in tissue properties distinguishing between healthy and malignant condition. SAR analysis demonstrates distinct characteristics in the presence of tumor compared to its absence, which reveals which is crucial for tumor localization. Therefore, the proposed antenna sensor emerges as a promising candidate for breast tumor detection, which is conformable with adequate sensitivity and compact dimensions. Thank you.